Unit 5, we're talking about market interventions, or the ways in which governments and nonprofits intervene into the market to try and correct some of those market failures that we talked about in the last unit. Now, typically with government, that intervention looks like policies, new policies or regulation that they put into place to try and correct some of those some of those failures. But for governments and nonprofits, it might also look like a new program that's put in place to try and help some of the people who are impacted by some of those market failures. So, along with trying to understand what types of policies or programs are put into place, we also want to give you the tools to be able to assess whether a policy or program is doing what it's intended to do. Because with the law of unintended consequences, the intents or the goals of the program are not the same as its effects. And so we want to be able to actually measure and assess whether the policy or program is doing the things that we intended to do. So in these videos for this unit, I'm going to be walking through some statistical models that help us to be able to do that. Now, one of the dangers that we run into with using statistical models, you've probably heard the phrase correlation is not causation. Not every statistical model, even if we have lots of data, not every statistical model establishes causation, that the policy is what's causing an increase or a decrease in some kind of observable characteristic. We might only be able to look at associations. So for example, if we have a time period and if we have a treatment that occurs here in the middle, I can't just compare the pre-treatment group to the post-treatment group. Why? Well, that shows that there might be associations between the two groups, but it might not be the policy that leads to any changes before and after. It could be other things that occurred that cause in part some of the differentiation between the pre-group and the post-group. But if what we do then is if we add a control group, so if we find another group where the two groups are trending, the treatment and control are trending in the similar direction, and then we have a policy intervention. And then after that intervention, they no longer start to trend the same way. Now we begin to have a causal claim to say, we can assume that these would have continued to trend the same way if the policy hadn't occurred. But because after the policy is implemented, they no longer start to trend the same way, we can infer that it was the policy that caused the change in that trend. So this is again called a difference in difference design. So let's jump into a practice problem here to see how we design this, and then the statistical tools that we use to be able to assess how much of a difference the policy made.
Okay, the problem reads, suppose that the state of Deseret introduced a new public health policy in July of 2020 aimed at reducing obesity rates by subsidizing healthier foods in grocery stores and increasing public awareness about nutrition. We want to evaluate whether the policy had a significant impact on reducing the average body mass index, BMI, of the state's residents. Suppose that Deseret's neighboring state, Ensign, did not implement such a policy. Okay, good. So again, in this situation, we're wanting to understand if this policy had some kind of an effect on average BMI in the state. And we're going to be able to exploit the fact that its neighboring state, Ensign, didn't implement a policy which we can use as a control group here. So the first thing that we're going to want to do is we're going to want to just graph the data here. So we have the average BMIs by month for the state of Deseret, and then also down here for the same time period for the state of Ensign. So the first thing to do to graph it here is we're going to select the month and for all of the years or all of the month periods for Deseret. And then we're going to select all of the BMIs for the same time period. And for this one, I know we've used a scatter plot with lines for a lot of our graphs so far. For this, I think it's actually easier to just use a line graph the way we're calculating it here. Okay, so here is for the state of Deseret what the average BMI looks like trending over time. Now, we don't just want to graph Deseret, we also want to graph Ensign, which is our control group. So what we're going to do is we're going to right click and select data. And I'm going to add a new series here. That means essentially we're just going to add a new line onto the graph. And for the Y values here, I'm going to come down and select Ensign's BMI. Okay. So when I click OK here, now I've got both of these on the same graph. Now, the policy was implemented in July of 2020. So right here on the graph is where the policy was implemented. So the first thing we need to look at is we need to look at whether this design satisfies the parallel trends assumption. So again, in order for the causal argument to work here, we have to assume that these two groups are trending similarly before the intervention. So before this time period, are they trending similarly? Well, yeah, they're not perfect, but we can see that both of them are trending towards lower BMIs and that they're essentially a parallel trend here. So we're looking good there. Now we can already start to see the story here of what's happening, right? So the intervention happens here in July of 2020, and what starts to happen? The control group continues on this path, whereas the treatment group drops quite a bit. So what we want to do now is we want to measure, so we can make a causal claim here, right? So just looking at this, we can make a causal claim and say, well, definitely this seems to have had an effect, because assuming that they would have continued to trend similarly had the policy not happened, this led to a larger drop in BMI. But we also want to be able to measure the size of this effect. So a drop in what BMI is associated with this policy. So the way that we're going to do this is we're going to calculate the difference in differences. So it's this little formula right up here. So what we want is we want to calculate the average BMIs for 4 different groups. So we have the post-treated, so that's the blue line after the treatment. Pre-treated is the blue line before the treatment. And then post-control is the orange line after, pre-control is the orange line before. So we want the average BMIs for each of these 4 groups, and then we're going to subtract all of this from each other, and whatever's left over is the effect size of the policy. Okay, the first step in being able to calculate the average BMIs for each of these 4 groups is we're going to create a few of dummy variables. So when I say dummy variables, what I mean is we want to create just a binary variable that designates these groups, because we're going to use a regression model here, and a regression model can't process this qualitative information. So it can't just look at dates and determine whether it's in the pre-group or the post-group. So I need to create some kind of quantitative measure of whether it's in the pre-group or the post-group. So I'm going to start with, we're going to do a treat, so whether or not it's in the treatment. We're going to do a post, and then we're going to do treat times post, which we'll talk about here in just a little bit. Okay, so for the treatment variable, I want this to be 1 if it's in the treatment group and 0 if it's in the control group. Well, in this case, the treatment group is Deseret. So I'm going to use an if function. I'm going to say if this cell here is equal to Deseret, value if true, well, I want it to be a 1 if it's true. So if this is Deseret, then I want it to be 1. Value if false, I want it to be a 0. Okay. And I can go ahead and just click this all the way down. It's going to put 1s for all Deseret and 0s for Ensign. Okay. The next one is post. So here I want this to be a 0 if it's in the pre-group and a 1 if it's in the post-group. Well, trying to code an if function for this one would be extremely difficult. So I think this one's actually just easier to just put 0 and just look at the dates. So if it's in the pre-group, so anything before July of 2020, need one more, it's going to be 0. Anything after July of 2020 is going to be 1. Now, with that being said, what do we do with July of 2020? Is it a 0 or is it a 1? Well, it's actually neither, because we want this to be a clean break between the pre and the post group. July 2020 is our policy window. It's ambiguous, and so what we're going to do is we're actually going to just delete this from the analysis, because we're not sure at what point in the month that it was implemented, and so we just want a clean break before and after. So the policy window will just delete out of the analysis. Okay, now we're going over to Ensign, so back to 0 in the pre-group. So as long as it's before July of 2020, okay, to 0. And then again, I'm going to delete July of 2020, and the rest are going to be 1s. Okay, so now that gives us a quantitative measure of all 4 of these groups, right? Pre and post in this one, and treatment and control in this one. So 1, 0, 1, 0. Now the last one I want to do, and we'll talk more about why we use this, is I want to do treat times post. So this is just a variable that multiplies treatment times post. And what it's really capturing is just the group that is both treatment and post. It's this blue line over here after post. And so what we're going to do in the regression model is we want to measure the effect of being in this group while controlling for all of the other groups. We'll talk more about that here in just a second. Okay, so we have all of our dummy variables here. So now the way that we can calculate the averages for each of these 4 groups is through a pivot table. So we'll go ahead and insert a pivot table here. For the range, we're going to select this entire table here, including our dummy variables. And then we can select where we want to put this thing. And I think that's great. Okay, so I'm going to hit OK. The pivot table field will come up. And remember that a pivot table allows us to choose what we want. So I'll take all of this data in this big table, and then I can choose what I want to be in my columns and my rows and the value or the statistic that I want it to calculate. So if we remember, I want average BMIs. That's what I want for each of these groups. So I'm going to put BMI, and I'm going to change this to average. So it's saying I want you to calculate the average BMIs. And the 2 groups that I want are treatment. So we'll put treatment as a row, and we'll put post as a column. So now you can see it provides this little 2x2 table. So for each of these groups, so this is our control pre, this is our control post, and then this is our treatment pre and our treatment post. So we have these average BMIs for each of these 4 groups now, and all that's left to do is to plug these in and solve. So let's do our first difference, which is the post-treated minus pre-treated, and then we'll do our second difference, the post-control minus the pre-control, and then we'll calculate the difference in differences. That's where the name of this design comes, where we subtract the 2. So let's start with the first. So remember, treatment is on the row and post is on top. So I want post, which is 1 on top, and treated. Okay, so I want this here. So I'm going to say equals 1, 1 for post-treated minus, and then I want pre-treated. Okay, so it'll be this one right here. And then the second one, the second difference here is post-control. So post-control minus pre-control. Okay. So we have each of our differences here. Now, one thing I'll just note, it actually mathematically doesn't matter if you subtract this minus this, and this minus this, or if you go this way, this minus this, this minus this. If you get it confused, it's going to be okay. Mathematically, it comes out to the same thing, okay? But we've got each of our first and second differences, so now we want to take the difference in differences. So we say equals this minus this. Okay. So here we go, we have our answer. So the size of the effect, the policy, it says that on average, being in the state with this policy led to a decrease in 1.22 BMI. Okay, so we have the effect size. The problem with this approach is that we don't know if this difference is statistically significant. If you'll remember from stats class, just because we're able to find that calculate some kind of difference, it may be that difference is just by chance. right? And so the idea of statistical significance is we want to come up with a p-value that will tell us the probability that this difference here, this result, is just according to chance. So the best way for us to get this same calculation, so we're going to be getting this same number here, I'm going to highlight it, but what we want is also to produce a p-value for this so that we know whether this difference is statistically significant. Well, we can do that using regression, okay? So for this, we will go to the Data tab, Data Analysis, and we'll select Regression. Okay, for our y variable here, our y variable is our dependent variable. It's the outcome variable, whatever we want to measure the effect of the policy on. So in this case, it's BMI. Okay, so we're going to select BMI here for our y range. And I selected the label here, so I made sure the labels option is selected. And then I'm also going to select for the x value, we want all of our dummy variables. Okay, perfect. Now, one thing to note with Excel is that the x variables all have to be next to each other, right next to each other. If there's something in between each of these, you're not going to be able to do it. That's kind of why we built it this way. They all need to be right next to each other for this to work in Excel. Okay, last thing, we'll just pick where we want this to put the output, and we'll select OK. Okay, so here are the outcomes of the regression here. Now, if you'll remember, a regression analysis will put out coefficients. These coefficients are what we care most about. The coefficients tell us for a 1 unit change in the independent variable, how much does the independent variable change? Well, if you'll notice this last variable here, treat times post, do you notice anything about this number? Well, it's the exact same as what we found in the difference in difference. So this treat times post, the effect of being in this group, of being a 1 in treat times post relative to being in any of the other groups, is 1.22. So regression gives you the same exact difference in difference when you use this interaction term, the treat times post. But it also gives us right here a p-value. So now we can assess whether this is statistically significant. So in this case, now this is in scientific notation. This E minus 11 means that there are 11 zeros before these numbers here. So this is a very, very small value. Now remember, the p-value is the probability that this finding, this difference, is according to chance. So if this is really, really low, that means the likelihood that this happening just by chance is very small. So it's more likely that this is just a statistical difference. It means that the policy had a statistically significant effect. Okay, but this is 2 different ways to be able to calculate the difference in differences. Hopefully you can kind of gather from this why this is so useful. So anytime we have some kind of policy intervention and we have data in a pre-period and a post-period, and if we're able to find some kind of control group that trends similarly before the treatment, then a difference in difference design is a great way to be able to assess the impact that a policy is having. We'll practice this more in class. We'll go over another example so that you can kind of get used to how we calculate this. But hopefully this is helpful for understanding how we design it.